Right. So today's class will be discussing about this property of liquids called surface tension and the effects that it produces. Okay. So remember that surface tension is a property of liquids only. You don't observe this in gases. Fine. And you must have observed these in daily life, like tiny, very light insects. Okay. They are simply able to stand on water. Yeah, or you can call it sit on water also. And you may also have observed that threads, okay, thread can float maybe. Uh, Even a metal wire, if it is light enough, it can float on water. Fine. What I mean by light enough is, see, metal is obviously denser than water. For example, steel. Steel is denser than water. A ball made of steel will definitely sink into water. But if you take a thin wire made of steel and gently place it on the surface of water, you can find it floating. Fine. So these happen due to surface tension. Now, as you can see from these pictures, fine. Look at the first one where the insect is standing on the surface of the liquid. You can see these depressions on the surface of the liquid wherever its weight is getting supported. Okay. You can see the depressions on the surface of the liquid. Now, what do they look like? It feels as if the insect is sitting or standing on a membrane, like a sheet. Okay. So that's the idea behind surface tension. Basically, what happens is the surface of a liquid, okay, the free surface of a liquid behaves like a stretched membrane. Fine. Now, why it behaves like that and how to find out the force that it exerts, how to make use of it, how to explain some phenomena based on it is what we'll be discussing in this part of the chapter. Right. Okay. Consider some liquid in a container. Fine. Obviously, there will be some liquid molecules very close to the surface of the container. Okay, sorry, surface of the liquid. So let's consider one such molecule. We call this as a surface molecule. Okay. And there will be many molecules well within the liquid. Okay. We call them as molecules in the bulk of the liquid. Okay. So surface molecules and molecules in the bulk of the liquid. These are the two types. Fine. Now, these molecules are surrounded by other molecules. Now you look at the surface molecule. The surface molecule is surrounded by similar molecules, that is liquid molecules on one side, but on the other side, it's surrounded by air molecules. Fine? Air or whatever is present outside. So its surroundings are not uniform. But if you look at the molecule which is in the bulk of the liquid, it is surrounded by like molecules on all sides. Okay, so there is a difference in the surroundings of the surface molecule and the molecule in the bulk of the liquid. Okay, now between liquid molecules, now have any of you observed this? Tell me from your everyday experience. When two water drops are brought very close to each other or into contact with each other, what happens? Do they stay as two separate water drops, or what do you see happening? When two water drops are brought very close to each other or brought into contact with each other, what do you observe happening? Aishwarya, what happens?
Sir, it becomes a
Okay, your voice is breaking. It was not clear. You can type your answer. Vanilla, you tell me what happens.
they both will merge and become one large drop of
They
liquid.
merge and become a slightly bigger drop, somewhat like this. Okay, so this means that, or this suggests that liquid molecules want to stay together. Want to stay together means what? They have some attractive force among themselves. So you observe the forces experienced by the molecule on the surface and the molecule in the bulk of the liquid. The molecule on the surface is surrounded by like molecules only on one side. Fine. On the upper side, there are air molecules or gas molecules. They may not be exerting much attractive force on this liquid molecule. Okay. So this molecule A experiences attractive forces only from one side effectively. Okay. Let's call this molecule as A. The one in the bulk of the liquid, let's call it as B. Whereas B, if you observe, experiences attractive forces from the surrounding molecules in all directions. Okay. So you all tell me, relatively, which of these molecules is stable, A or B? Is the surface molecule more stable or the molecule in the bulk of the liquid more stable?
The B is more stable.
B is more stable because it is surrounded by, kind of surrounded by its friends on all sides. A has friends only on one side, on the other side it is exposed. Okay. So A is kind of restless or unstable, you can say. So A is a molecule on the surface. B is a molecule in the bulk of the liquid. Okay. Now we know, we can tell that A is relatively unstable compared to B. Okay. Generally, okay, you might have learned in chemistry also. What does being unstable mean? Does it mean the system has high energy or low energy?
High energy.
High energy. Okay. So surface molecule has relatively higher amount of energy compared to the molecule in the bulk of the liquid. Okay. So all the surface molecules will be relatively unstable compared to molecules in the bulk of the liquid. Relatively unstable means having more energy. So that extra energy, fine, the excess energy possessed by surface molecules compared to energy of molecules in the bulk. Any idea what this is called? It's called surface energy of the liquid. Okay, which we will now denote by the symbol U. Right? So surface molecules being relatively unstable are at a higher energy compared to the molecules in the bulk. That extra amount of energy which the surface molecules have is called surface energy. I'm not talking about energy stored by each molecule. The entire surface means all molecules of the surface together, whatever extra energy they store, that combined energy is what you call as surface energy. Okay. Now, it's obvious that more the number of molecules on the surface means more the exposed molecules, greater will be the instability. Okay, every molecule which is on the surface is relatively unstable compared to molecules which are inside the liquid. If there are 10 molecules, you'll have 10x amount of energy. If there are 100 molecules on the surface exposed to air, you'll have 100x amount of energy. Okay, so remember that surface energy is proportional to number of molecules on the surface. Okay, because greater the number of surface molecules, greater the number of unstable molecules. That's all. Okay, therefore, it automatically becomes proportional to area of the surface. Okay, there are some other factors also on which it depends. Obviously, it depends on the liquid. Okay, how strong the surrounding molecules are trying to pull the surface molecule in. Okay, it depends on that factor as well. So it depends on how strong the liquid molecules attract each other. So it depends on intermolecular attraction as well. So remember the factors on which surface energy depends. If they want to ask you conceptual questions, they can ask like this. So basically it depends on the number of surface molecules, and Where does this energy actually come from, or why are they unstable? Because they are surrounded by like molecules only on one side. What if they are surrounded only on one side? They will be having attractive forces. That force is the cause of this extra energy. Okay. So stronger that attractive force between the liquid molecules, stronger will be the surface energy. Depends on that factor as well. How to include that factor, you will understand after we discuss surface tension. Okay. So it's understood for now that surface molecules are at higher energy compared to molecules in the bulk. Okay. Now you all tell me, uh, if you put a small drop of water on a horizontal surface, what shape do you see it taking? Let's say there's a horizontal surface like this, and you put a small amount of water on it. What shape does it form into or adjust into?
Yes, sir.
Vanilla, what did you say?
A hemisphere, sir.
Hemisphere. Okay, okay. Kind of. It depends on the material on which it is placed actually. It might look like a hemisphere as well. Now, you all may have observed dewdrops, right? This is a very good picture actually. It looks like the drop is almost not even in contact with the leaf. Just there are only a few points of contact. It's trying to become a sphere. It's not a perfect sphere because gravity will be acting in the downward direction. Some deformation will occur, but it wants to become a sphere. Okay. It's always like that. Liquid wants to stay in a spherical shape, but due to gravity and some other factors, it gets deformed. Raindrops also, okay, when they fall in vacuum, they are almost like spherical. But when they fall through air, due to air resistance, the drop shape gets disturbed. That's okay. But they want to be spheres. Okay, it's a general nature of liquids. But why do you think it is so? Why do liquids always want to take spherical shape? Any guesses? Okay, tell me this. For a given volume, okay, suppose volume is fixed. Let's say volume of liquid is fixed. For a given volume, you can take a volume of clay also, doesn't matter. You can make different shapes out of it, right? You can make a cube, cuboid, cylinder, sphere, many shapes you can think of. You may have learned this in mathematics. For a given volume, which shape has the least surface area? Okay, I think you'll learn this in application of derivatives. You'll learn minimum surface area. Which shape has the least surface area? Any idea? Sphere. Okay, correct. And we see that liquids always tend to become spheres. Means liquid always tries to take or assume the least possible surface area. Why did I write idea? Okay. Liquids always try to assume the least possible surface area. Means they want to decrease their surface area. And the reason is obvious. Any system naturally will move to a state of lower energy. Now, molecules on the surface of the liquid have higher energy compared to molecules in the bulk, right? So, if the liquid can somehow send more molecules into the bulk and decrease the number of surface molecules, obviously its surface energy will decrease. Okay, surface energy is proportional to number of molecules. No, lesser the number of molecules on the surface, lesser the surface energy. Means lesser the area of the surface, lesser will be the surface energy. Means greater will be the stability of the drop. Okay. Now you all must have seen, like consider a cricket match, football match, whatever it is. Before the start of the match or the start of the innings, the players get into a huddle. Okay. Like they form a circle. Why do they form a circle? Why can't they stand in a line? Any guess? Okay. Simple reason. See, they want to be heard, right? They want to hear what the other player is saying. They want to ensure that they themselves are heard also. So the distance between the players has to be reduced. They have to stay close to each other. Now the number of players is fixed. Suppose it's a cricket match, fielding team, 11 players will be on the field. Okay. They all want to stay as close as possible to each other, so they form a circle. Fine. In any other shape, the distance between players or the total length would be more. Fine. Uh, Same thing happens in 3D. If you visualize, it becomes a sphere. So basically, if things want to stay together, they tend to become spheres. That is why planets are spheres. Moon is spherical because of that reason only. Okay. See, when the Big Bang happened, we all believe planets and all formed, asteroids, planets and all formed out of the Big Bang. When the Big Bang happened, there's no guarantee that all these planets and all the fragments that broke out were in spherical shape. Why will they be perfect rounds? Okay. Perfect spheres. Not necessary. But over time, see, you consider a planet. Planet is a collection of very large number of molecules, right? Now, gravitational force brings them together. Okay, so every particle of the planet is attracting every other particle by means of gravitational force. So all the particles of the planet have a tendency to stay as close as possible. So automatically they become spherical in shape. Okay, so basically, if there is a system in which all particles attract all particles, they will naturally become spheres unless they are disturbed by external agents. Okay. So same thing happens with the liquid also. Liquid intermolecular attraction will be there. So liquid tends to become a sphere. And in that process, it reduces its surface area. Lesser the surface area, lesser the surface energy. Okay. Now, how in this process of reducing surface area, another interesting thing happens. Now, you all consider this just a moment. Okay. Consider a stuffed toy, a stuffed toy or soft toy. Basically, as the name suggests, it has cotton or sponge stuffed inside it, and on the outside there is a cloth which covers it. Okay, just a moment. A pillow also you can consider. You can even consider a stuffed rugby ball made like this. It looks like this is made out of cloth. Fine. So basically, there is cotton stuffed inside, and I mean, it's covered up with a layer of cloth, and you can see the stitches as well. Okay, observe that rugby ball picture. What do you think will happen if we cut open these stitches? What will happen to the ball or the cloth covering the cotton? What will happen to the cloth is what I'm asking. If we cut these stitches, what will you observe? Hey, try to guess something at least. What do you think will happen if we cut those stitches?
No, the cotton will come.
Ha. Okay. You can even consider a pencil pouch. Those cloth pouches will be there, no, with zips. Suppose you stuff it with paper, cotton, cloth, whatever it is, and tightly close the zip. Okay. When the zip is closed, it will appear cylindrical. The pouch will appear cylindrical. But when you open the zip, what will happen? The edges of the zip will separate. So basically, what you will see happening here with the rugby ball is something like this. Okay, you said the cotton will come out. That's correct only. Fine. So, okay, this is all the surface of the ball. and in between, whatever cotton cloth, whatever is stuffed inside, you will be able to see it. So basically what is happening is, okay, one more thing I want to ask. This cloth has a certain surface area, right? When you cut these stitches open, the cloth area will remain the same. It's not like the cloth shrinks significantly. The cloth area remains same. There is extra gap created here. Okay. So the overall surface area is increasing. Okay. Most of the cotton will be covered by cloth, but some cotton will be exposed to air when you cut these stitches. Okay. So basically, what were these stitches helping with? These stitches were helping reduce the surface area. Okay, they were covering the exposed cotton. Do you understand that or not? Vanilla and Aishwarya. The stitches were helping in reducing the exposed area. Yes or no? Think carefully. Ask me if you have any doubt. This point is important. So basically, what is happening? You can consider it like this. Imagine there is one molecule here and one molecule here. They are both being tied by this string. Okay, they are both being held together by this string. Okay, so this, fine, I'll mark them in yellow, orange. No, orange is not visible. Let's mark them in red. Yeah. So one of them experiences a force this way, the other one experiences force this way. They are being held together by that string, which is used to make those stitches. Same happens with other molecules as well, not just those two. We will just randomly visualize a few. These two molecules also, or particles also, they are pulled towards each other by this string, by the tension in the string. Okay, so now we are like getting closer to the definition of surface tension. So you can consider any two molecules on that line, on either side of that line. One molecule on this side of the line, and other molecule on the other side of the line. So they'll be held together by the stitches. Okay, so what are these stitches doing? These stitches are helping in reduce the overall surface area of the ball. Okay, ball, pillow, soft toy, stuffed toy, whatever it is. Had the stitches not been there, you would have seen some area exposed. Because of the stitches, the surface area is decreasing. Now, a liquid also naturally tends to decrease its surface area. So, in that process of trying to decrease its surface area, what happens is the surface of a liquid effectively behaves like a stretched membrane, like a tight membrane. It behaves like that. Okay, you can say it is a result of that intermolecular forces between the surface molecule. Like for example, we considered this molecule here, let's call it as X. X was being pulled on one side by one molecule, on the other side by another molecule. So it has pulling forces on either sides. It is attracted to the adjacent molecules. Similarly, you consider another one here. These two also will be attracting each other. Okay, one force acts this way, one force acts this way. So those forces will be there between surface molecules. So as a result, it's like all the surface molecules are holding hands and pulling their neighbors towards themselves. Okay. So effectively, it behaves like a stretched membrane. The surface behaves like a stretched membrane. That is how the liquid actually successfully reduces its area, surface area. Fine. So consider a stretched membrane like this. Let's say there's a rubber sheet. Fine. Or that rugby ball itself you can consider. Assume it is being pulled by some forces at the corners, and it has taken a shape like this. Okay, you can consider this rugby ball itself. Now, depending on how tightly it is stitched, there will be a certain tension force acting between any two opposite molecules. Okay, any two molecules on the opposite sides of this line. Right. Now, the force exerted by one molecule on the other molecule depends on tension in the string. Let's say tension in the string, or okay, let's not give any values. Force exerted by one molecule on the opposite molecule depends on tension in the string. Now, if you consider the set of molecules, okay, here and the set of molecules here, force exerted by each molecule depends on tension in the string. That's fine. What about force exerted by all molecules on one side, on all molecules on the other side? What else will it depend on? The total force exerted by molecules on one side, on molecules on the other side. What will it depend on? Think carefully and answer. Okay, I got one answer as number of molecules. That is correct. Okay. Each molecule exerts a certain amount of force, then the total force exerted by one side on the other side definitely depends on the number of molecules. Okay. Total force depends. Fine. Now you consider a stretched sheet like this. Stretched rubber sheet. Okay. Now, what happens if you make a cut anywhere? Okay, let's say you make a cut like this from here to here. What you will observe is that the molecules get separated like this. Okay, you'll see an opening in the sheet, right? This is what we'll observe. Fine. So look at this imaginary, look at this line that I have drawn, the gray line. Before the cut was made, you consider molecules on one side and molecules on the opposite side of the cut. They are there, the molecules are there anyway. Okay. They were holding each other also. It's not necessary that one molecule is attracted by only one molecule. You can imagine connections like this one and this one, this one and this one also. So this one, this with this, and so on. Okay, molecules on one side attracted by molecules on the other side. So you can imagine it like this. These are all the intermolecular forces that I have indicated. So when you make a cut, what you are doing is you are breaking all those intermolecular bonds. I should not use the word bond. You are uh, removing all those intermolecular attractive forces. So then what will happen? The molecules will separate automatically. You may ask, why will they separate? Because these molecules are being pulled by the surrounding molecules, no, on each side. Okay. These forces will be attracting them. Okay. So if you make a cut, the left side molecules will go to the left side, right side molecules will go to the right side. Are you all able to visualize this? Any doubt in this? Okay. So before the cut is made, there were forces acting. Molecules on one side were exerting forces on molecules on the other side. When the cut is made, those forces are broken. So the molecules lose contact and a gap gets created between them. Okay. So remember, you take any imaginary line on a stretched sheet. Okay. This gray line that I have drawn is an imaginary line. Now, what is happening here? One side of the line one side of the line is attracting the other side of the line. Okay. So on the right side, okay, the forces will be like this to the left. The molecules which are on the right side, the forces on them will be to the left. And the molecules which are on the left side, the forces on them will be to the right. That is why they separate. Okay. When you make the cut, these forces are broken, so the molecules separate. Okay. Now you consider another imaginary line like this. Now, if you cut it along this line also, you will see particles separating perpendicular to this line. What does that mean? Before making the cut, there were forces acting like this. One side being attracted by the opposite side. Now, what is the direction of these forces? You see, I mean, you can clearly observe that the direction of these forces is perpendicular to the imaginary line. Okay, actually, every molecule there on that sheet is surrounded by molecules on all sides. No, so attractive force will be there on all sides. Which side it moves depends on which side you make the cut. Okay, for example, let's say there is an object here which is being pulled in four different directions. Net force is zero; it will stay there only. But if you remove one of these forces, then you will see it moving in the opposite direction. That is what happens with molecules on a stretched sheet. Okay. So remember, every molecule experiences force in all directions. Now, total force exerted by one side of the line on the other side of the line obviously depends on the length of the line, because longer the line, greater the number of molecules involved. Okay, so total force obviously depends on the length of the line. So force exerted by one side of an imaginary line on a liquid surface on molecules. Okay, we said one side. Actually, force exerted by molecules on one side of an imaginary line on a liquid surface on molecules on the opposite side is proportional to the length of the line. Why? Because greater the length of the line, greater will be the number of molecules involved. So total force is proportional to length, but force per unit length will become constant. Okay, or I should properly call it uniform. It will be the same everywhere. And this uniform term that is there, it's a property of that liquid. It varies from liquid to liquid. And this is what we call surface tension. This property is what we call surface tension. So remember, surface tension is not like the usual tension that we consider. Like tension is one of the common forces that we consider, right? That tension is a force. But surface tension is not force, it is force per unit length, where force per unit length acting perpendicular to any imaginary line you draw on a liquid surface. Okay. So, I mean, this definition is very important, and how you apply this is also very important. So, surface tension, let us denote it by the symbol T. You can say that T is equal to F by L, force per unit length. But this is a very specific, I mean, this formula is applicable to a very specific case. This is applicable only when the length is straight. Only when the length L is straight. What if it is not straight? Okay, this is where the like more finer details come out. Surface tension is actually force acting per unit length, that is fine, but if the length is not straight, you will have to consider it this way, dF by dL. Okay, on a small length, whatever is the force acting, divide them, you'll get surface tension. And from this itself, you can say that force acting on a small element of the length is equal to surface tension multiplied with the length. And if you want total force acting on a certain length, whether it's straight or curved, you will have to do integral of these forces, and forces are vector quantities. You need to be very careful. So this is something like how we derived force due to pressure, force on a surface due to pressure, because pressure is perpendicular force per unit area. Fine. Force is pressure multiplied with area. But what if the pressure is not same everywhere? Or what if the area is not flat? How do you calculate force? Fine. So something similar ideas we'll have to apply here. So remember, this force dF is equal to TdL. Okay, this is the most important thing in today's lecture actually. Acts perpendicular to the length dl. What is this length dl? Any small length you consider on the surface of the liquid, even at the boundary of the surface. Okay. So suppose there is, fine, I'm sure you all must have like played with those bubble, what is it? Played with that bubble liquid, making bubbles and all. Just a moment, I'll download one picture. Okay, fine, we don't have to waste time on that. Suppose there's a ring, okay? So basically what you do is you dip a ring into bubble solution, take it out. Then what you will see is a film of soap solution formed on the ring. Okay, formed in the ring. Okay. Now what happens here is this film of soap solution is it's a surface, right? It's an exposed liquid is exposed to air. So what will be happening? That film will be exerting forces everywhere on the boundary like this. Fine. You can try this experiment also. It has to be performed very gently. You take a bangle, okay, or a rigid circular object, dip it into soap solution, thick soap solution, and take it out. So what you will see is that a film of soap solution forms in the within the bangle or the circular object that you took. Next, what you should do is gently, okay, like first make a thread wet with the same liquid, okay, and that wet thread you tie it into a loop, and that wet loop of thread you gently place on this film of soap solution. It will take a random shape depending on the loop of thread. Okay, what all it has been through before, it will take a random shape and it may even move around on that surface. Okay, now what should you do? You prick the film of soap solution in between. Okay, like inside that loop of thread, you prick the film of soap solution. Can any of you guess what happens? I'll give you some time. Just try to guess what happens. I'll try to show you a picture also. So what you will see is something like this. So here they have gone a step ahead. They have like restricted the motion of the loop of thread, okay, by tying it to the ring. And when you prick it in between, fine. So you see that the loop of thread becomes a circle. Why does this happen? Basically, the loop of thread that is there, it is surrounded by film of soap solution. Okay. So before we prick it, the film of soap solution, what it will be trying to do is it will be trying to decrease its surface area like this by exerting a force on this boundary. Okay, there will be forces acting on that boundary everywhere, and there will be forces acting on the other side also because there is film of soap solution on the other side as well. Okay, so something like this will be happening. Okay, we cannot see these forces obviously, but they will be acting. Now, if you prick the film of soap solution in between, what happens is all that surface inside the loop of thread disappears. That surface doesn't exist anymore. Okay. What do I mean by doesn't exist? We have, it's like you take this rubber sheet. Basically, what will happen if you tear it like this? The molecules will go to the sides. Okay. Something like that happens with the molecules of the liquid also. Okay. So when you prick the liquid surface within that loop, the molecules all go to the edges of the loop. Okay, they'll go to the thread, close to the thread. So those inside forces will disappear. Now what will you be left with? You'll only be left with these outside forces, forces pulling the loop outwards like this. Okay, as a result, it expands and takes a circular shape. Finally, that is how it settles. Okay, this happens in real life also. You can try it out if you want. Did you all understand? Any doubt in this? Okay, this is an example of a real case. I mean, this is a picture of a real case, right? So you can see that there is film of soap solution around the circular loop, but inside there is no film. Okay, it has been pricked there. Okay, so basically, you need to understand the behavior of force due to surface tension. As I said, surface tension is not a force. Surface tension is the tendency of a liquid surface to behave like a stretched membrane. That property is what we call surface tension. Okay, mathematically, it is the force per unit length acting perpendicular to any line that you imagine on the surface. So if the line is curved like this is how you deal with it. You have to take elemental forces on each small part of the line. And due to those forces, if the line is flexible, the line will move also. So this loop of thread becomes a circle because the loop of thread is flexible. If it is rigid, it will stay like that. Liquid cannot change its shape if it is rigid. Okay. So let's spend some time on this. We will solve problems where we calculate the force due to surface tension first. So by definition, surface tension is force per unit length. Okay. Quickly, all of you give answers for SI unit and dimensional formula of surface tension. I'll give you 1 minute. Right. So obviously the SI unit will be Newton per meter and the dimensional formula mLT per minus 2 divided by L. MT per minus 2. So they can express it as kg per second square also, although it will not usually be done like that. Fine. Now let's briefly recollect how we calculated the force exerted by pressure on a surface. Okay, this is barometer. Okay, this is fluid. Yeah. So pressure by definition is perpendicular force per unit area. So suppose there is pressure acting over an area, how the area experiences force is perpendicular to every element of the area. Every small patch of area, you have to imagine small forces. The resultant of all those forces is the total force acting on that area. If the area is flat, okay, all those elemental forces will be in the same direction. It's very easy to calculate the net force due to pressure. Just pressure multiplied with area, or if pressure is non-uniform, integral PdA will give you the answer. You don't have to bother about vector addition of these forces because they are all in the same direction. What if all the forces are not in the same direction? We discussed this case where we found or derived force due to pressure on a hemispherical surface. We assumed pressure to be uniform, okay, but we had to find out the total force acting on it. Now on each small part of the surface, if you see forces in a different direction, every element experiences the same force, but the direction of the force is different. So you can't simply integrate magnitude of force and say this is the net force. So what did we do there? Let's briefly recollect. We first visualized the direction of resultant of all these forces. Since all of them have the same magnitude and there is a symmetric distribution, the direction of resultant had to be this in this particular example. Okay. So what we had to find out is the integral of x components of all these forces. Y, z components didn't matter. Okay. To get the x components of these forces, look at what we did. Force is pressure multiplied with area. Okay. So small force is pressure multiplied with small area. Small force as x component is pressure multiplied with area projection in the yz plane. Okay, because area in the yz plane is what gives rise to force in the x direction. Force is perpendicular to area, no? We want force in x direction, so you have to take area in the yz plane. You will have to deal with surface tension in a similar manner. Okay, force due to surface tension acts perpendicular to length. Force due to pressure acts perpendicular to area. Force due to surface tension acts perpendicular to the length. Okay, so you have to keep that point in mind, and based on that, you can answer. So let's see how many of you can solve this. Suppose there is a ring. We'll take a circular ring itself. Okay. Assume the ring's radius is r. And let's say the ring has a liquid surface inside it, a film of soap solution inside it. Okay. Now see, if you take a film of soap solution, you imagine a page of a notebook or one sheet of a notebook. One sheet has two faces. Okay, each face is called a page actually. Page number 1, page number 2 will be two faces of the same sheet. Fine. So one sheet has two faces, two pages. Similarly, one membrane will have two surfaces. So one film of soap solution, remember it has two surfaces. One surface towards you, one surface away from you. Towards you, the liquid molecules are exposed to air. On the other side also, the liquid molecules are exposed to air. So remember, there are two surfaces in one film of soap solution. Okay, one on each side. Both the surfaces will be trying to decrease their areas. As a result, what will happen? If you consider the boundary of this ring, the liquid which is in contact with the boundary will be exerting force on the ring like this. I will be indicating two forces at each point. Why? Because there are two surfaces. Fine. So at every point of the ring, there will be forces acting like this. Two forces acting. Okay. Now the ring obviously has circular symmetry. So the net force due to surface tension on the ring will be zero. For every element that experiences force due to surface tension, there is another element on the opposite side which experiences an equal and opposite force. So the net force on this ring due to surface tension is zero. That's fine. But suppose you consider only one half of the ring. Okay, let's take only the right half of the ring. Just a moment. Let's consider only the right half of the ring like this. As I said, ring's radius is r and surface tension is T. There are two surfaces, keep that point also in mind. Okay. Now surface tension by definition is force per unit length. So you take it as dF by dl. So how you can visualize it in cases where you want to find out the forces, consider an element like this. Okay, let's say the element's length is dl. Then the small force the element experiences, dF, is T multiplied with dl. Okay, and there are two forces on that element, no, one by each surface. So 2T dl will be the force experienced by it. So I'll write it directly. Force on each element is 2T dl. The 2 comes from the fact that there are two surfaces. Otherwise, it's just T dl. Okay. So we know how much is the force acting on each element. But we want the total force acting on this semicircle. Fine. Try to derive the magnitude, all of you. Let's call these forces as dF each. dF is 2T dl because there are two surfaces. Okay, so you take it as 2T dl. Derive the net force due to surface tension acting on one semicircle. I'll give you all 2 minutes. Try. Okay, listen. I already gave you a hint. I told you that the way we deal with it is similar to how we dealt with force exerted by pressure. Okay. So we'll try to find out. See, the problem here is we know the magnitude of each elemental force. dF is 2T dl. Okay. But the total force cannot simply be taken as integral dF. You can't simply integrate the magnitudes of small forces to get the total force. Why? Because the small forces are in different directions. Okay, each small force is in a different direction. So simply integrating magnitude will not work. You will have to integrate their components separately. Okay, let's see which components matter and which components don't matter. Can any one of you tell me, like you all visualize DFs acting on every element? Okay, starting from this one. Can any of you visualize and tell me the direction of total force due to surface tension acting on this semicircle? What will be the direction of the resultant of all these small df's? Aishwarya, what do you think?
Negative x direction.
To the left, negative x direction. Good. So there's no point integrating the other components of these forces. They are going to get cancelled. Their y components are going to get cancelled, assuming this film of soap solution is in the xy plane. Only their x components will survive. Okay. So what we need is the x component of the force. Now you can't change surface tension. Surface tension is a property of the liquid. Okay, it depends on how tightly liquid molecules hold each other. So from liquid to liquid, it can vary. So 2T. To get force in x direction, you know force due to surface tension acts perpendicular to the element. Okay. To get force in x direction, obviously you will have to take the y component of the length. That's all. Okay. So imagine projecting these lengths onto the y-axis. For one, it will be this much. For another element, it will be quite large, like this. For another element, it will be like this. Okay. But whatever it is, you project the entire curved length onto the y-axis, you get a straight length like this. Can any of you quickly tell me how much this length would be? When that entire wire is projected onto the y-axis, how much would its length be? We are not opening the wire up and placing it along the y-axis. It's like casting its shadow on the y-axis. Okay, projection only. We are not opening it up. Fine. So can any of you tell me how much or how long this projection would be? It's very easy. You know the radius of the ring. Based on that, you tell.
So, but when you project a hemisphere, we get a circle.
Yeah, when you project a hemisphere, you get a circle. This is not hemisphere. It's a circle, semicircle. When you project semicircle, it forms a line, no?
Okay.
What will be the length of that line?
You also.
2 times the radius, correct? 2r. That's all. Okay. Now, to get total force due to surface tension in x direction, you will be integrating the small forces in the x direction. So you will be integrating 2t. Okay, you'll put the 2t aside and you'll be integrating the length components in the y direction. When you add all the length components in the y direction, it becomes 2r. Therefore, it becomes 2t multiplied with 2r. Or to simplify it, I'll write it this way. The first two comes from the fact that there are two surfaces. Okay, that's fine. We'll put it aside. Multiplied with T into 2R. T is surface tension. 2R is the length perpendicular to the force due to surface tension. Force due to surface tension was in the x direction. So we had to consider length in the y direction. That is what matters. Okay. So remember, this is how you properly calculate force due to surface tension on any boundary. Okay. If it's a straight boundary, it's very easy because all the df's will be in the same direction. You can integrate them directly. If it's a curved boundary, you need to be careful. Okay. So basically, surface tension is a property of liquids. It depends on how tightly the molecules hold each other. Now, at the beginning of this session, we had discussed about something called surface energy, the extra energy which surface molecules have compared to the molecules in the bulk. And there are two factors that we discussed. It depends on the area of the surface, that is the number of molecules on the surface. Both are one and the same. It also depends on how tightly the molecules are pulling each other, attracting each other. Means it should depend on surface tension. Okay, let's derive how surface energy depends on surface tension. Questions based on this are very common and this is important to know also. So relation between surface tension and surface energy. Okay. There is a like very common idea that we use. Consider a wire frame like this. Okay, a metallic frame, thin metallic frame only, but it is rigid. You can't change its shape. Okay. And assume there is a wire which you can freely slide on this metal frame, on the parallel rails of this metal frame. Fine. Now dip this apparatus into soap solution and take it out. If you dip this apparatus into soap solution and take it out, what you will see is a film of soap solution forming here. Okay. Now, film of soap solution has surfaces. Liquid tries to decrease its surface area. As a result, what the liquid will do is it will exert forces on every point of this boundary, even this sliding wire. So what happens if you release that sliding wire freely, it will move to the left. It will move to the left, the liquid surface area will decrease. In fact, the wire will go completely to this end. All the liquid will form into a drop and it may fall off also. The drop may fall down also. Okay, that is what you will observe to happen. Okay, that is what you will observe happening, right? But if you apply an additional force, you can hold that wire there. You can prevent it from moving. How much force do you have to apply? Whatever force surface tension is applying in the opposite direction, you will have to oppose that. Okay. Now, film of soap solution has two surfaces. Let's say the length of this sliding wire is L. Now, each element experiences a small force. That small force dF can be written as T into dl because T is dF by dl. So dF can be written as TdL. All the TdLs are in the same direction. And remember, there are two surfaces. So the total force experienced by that wire, sliding wire, will be 2 times surface tension multiplied with the length. Okay. Integral dl will become L because it's a straight length. You can integrate the forces directly. But there are two surfaces, no? So 2TL will be the force. So if you want to keep that wire in equilibrium, you will have to apply a force of 2TL in the opposite direction. And any force just slightly greater than this can slide the wire in the opposite direction. Why should we slide the wire in the opposite direction? If you slide the wire to the right gently, you will be increasing or you will end up increasing the surface area of this film of soap solution. So imagine sliding that wire gently to the right. Let's say we applied a force just slightly greater than 2TL, almost equal to 2TL. Okay. So we are slowly expanding that liquid surface. This is what you will see happening. There will be forces acting here now. Okay. So we applied a force almost equal to 2TL and did this. So let's assume you expanded the area or you expanded the surface by a distance x. Now the length of that sliding wire is L. You pulled it aside by x. So what you effectively did is you created new surface. How much? This rectangle. Okay. So the new area created is x into L. But you are expanding a film of soap solution. No. So basically you are expanding two surfaces, not one surface. Therefore, the new surface area created is 2 times of XL. That much new surface has been created. Okay, let it be. So let's call this as area. To create this area, what did we do? We pulled the wire aside by applying a force of 2TL. How much did we pull the wire? We pulled it by a distance x. When a force pulls an object by a certain distance, it will be doing work. Work done by us in this process will be the force exerted by us 2TL. Actually, the force exerted by us is just slightly greater than 2TL. We can equate it to 2TL. Multiplied with the displacement in the same direction as the force is x. Okay, so 2TL into x. Doing work means what? Supplying energy. We supplied this much energy to create this much area. Okay, so what can we say? This much area has this much energy. Okay, so 2xl area has a surface energy of 2xl multiplied with T. That's all. Therefore, the formula for surface energy becomes, see 2xl here is area. So surface energy is just surface area multiplied with surface tension. U is equal to AT. Simple. Okay, and this proves the fact that the total surface energy of a liquid depends on its area and the intermolecular attraction between its molecules. Okay, which is given by surface tension. Okay, so we'll stop it here for today. So we basically discussed what is surface energy. Okay. Yeah, what is surface tension? What is surface energy? How surface tension arises due to intermolecular forces that we discussed. And then a formula for surface tension dF by dl and its application to find out the total force. And finally, relation between surface energy, surface area, and surface tension. Okay. Next class, which will be tomorrow itself, we will solve problems based on all this. And if time permits, we will move forward also. Next thing we need to discuss in this is excess pressure in a soap bubble, liquid drop, and all those things. Okay. Thank you all. We'll continue in tomorrow's class.
Thank you.